We are wrapping up Unit 7, looking at one other theory, which is molecular orbital theory. And really what we're doing is we're looking at two complementary theories. We looked at the valence bond theory already, and now we're going to look at the molecular orbital theory, or MO theory. Now, I'm just going to go over the basics. You will see more of this in more detail with different examples in organic chemistry if you choose to proceed with the chemistry sequence. But we do need to know a couple of things at this point about molecular orbital theory. As a reminder, I have a couple of definitions written out already. As a reminder, we are comparing this with valence bond theory, and there's no better theory. There's no good, there's no bad. They're both true, and they both have their advantages. It just depends what you want to study when you look at these molecules, whether you use valence bond or molecular orbital theory. As a reminder, valence bond theory is picturing the molecule as a group of atoms that have these bonds that are made through the overlap of atomic orbitals, and in many cases, the overlap of hybrid orbitals. So we're looking at the orbitals on an atom and how they overlap with other orbitals in neighboring atoms. Essentially, the electrons are what's called localized. They are held within those bonds. MO is pretty abstract, and again, I'm going to tell you the basics, a foundation for when you go on to higher chemistry courses. Molecular orbital theory, you can still go to picture the molecule as a group of nuclei that have MOs, that have molecular orbitals, and many times we just call them MOs, that extend throughout the whole molecule. So in here, they are very dependent on using Schrodinger's equation, the wave functions, to calculate how these separate atoms come together to make not atomic orbitals, but to make molecular orbitals. And when you think of it that way, the electrons are delocalized. Actually, they are mobile throughout the whole molecule. Again, which one is more true than the other? That's not really a question that we should be asking. It's what do we want to study? So when you're looking at the geometry, valence bond theory is very good at predicting the molecular geometry. These are tools, right? These are tools by which to study molecules. Molecular orbital theory has its benefits when you study reactions. Reactions and spectral properties. Oops, properties. For instance, will a molecule absorb UV light? Will a molecule fluoresce? Will a molecule, if you pass electrical current, will it change color? Spectral properties. In terms of reactions, you're going to see in organic chemistry that molecular orbital theory, if you start populating what's called the antibonding orbitals. This is the first time that I've mentioned antibonding. A very unusual concept, just like you have matter and antimatter. We have bonding and antibonding, and definitely I understand that antibonding is going to be a very abstract concept at first. Okay, so this video we're going to talk about MO theory. Now, I want to set at least one ground rule, and it's a very important one. Remember that in valence bond theory, if you hybridize or you mix a certain number of atomic orbitals, you will conserve those orbitals and you will get the same number of hybrid atomic orbitals. This is the idea of if you mix an S plus a P plus a P, you will get 3 sp2 orbitals. That, again, comes from the math of the Schrödinger equation, or commonly known as the wave functions. MO theory has the same guidelines. If you combine, or maybe we should use the word overlap. If you overlap n number, we're still going to start with atomic orbitals. But instead of making hybrid orbitals, we're going to see how do those atomic orbitals combine or overlap within the context of the molecule to make the same number of molecular orbitals. So that's the difference. We are looking at molecular orbitals. But we're still conserving orbitals. Okay, so for instance, let us take a look at H2. All right. Using valence bond theory, it's very simple, right? You have a s orbital, the one s orbital for one hydrogen, bonding or overlapping with the 1s orbital for another hydrogen. So the way I'm drawing this, I'm separating them a bit. And you each have one like this. With valence bond theory, you're bringing these two together to form a bond, right? To form this sigma bond right there. But MO is a little bit different. MO is we're going to try to visualize what are the molecular orbitals. And the way we draw that is we draw the MOs in the middle, pretending that these two are coming together. I know it's a little bit odd, but again, these are atomic orbitals, right? Atomic, atomic. Or simply AO for atomic orbitals. When you mix two atomic orbitals, or combine or overlap two atomic orbitals in MO theory, it's saying that you make the same number of MOs. And one is going to be higher in energy and one's going to be lower in energy. So they average out. So you have an MO, how do I want to do this? You have an MO down here, and you have an MO up here. And those are your two MOs. We are combining two atomic orbitals to make two MOs. Now, these have special names. Since we're combining the 1s orbitals, the molecular orbital down here, the more stable, is the sigma, and they use subscript, or most textbooks use subscript, sigma 1s. And yeah, that sigma means that you're making a bond where the electrons are in between the two nuclei, that they are in the axis of the bond axis, I mean. But up here, which is higher in energy, we have to have a second MO based on this guideline right here. And the second MO is higher in energy, and this is what's called the antibonding orbital. And we show that with an asterisk. But when you pronounce this, you say sigma star 1s. That's how you pronounce that orbital. And that's fine. You could probably tell by the name, antibonding. If we put electrons in the antibonding orbital, we are weakening the bond. But we only have two electrons to deal with for the whole molecule. So when we take a look at the MOs, those two electrons are in the sigma 1s. So I know the picture looks kind of cluttered, but really when you look at the molecule, you're only considering the MOs, that piece right there. But this is just a way to diagram what's happening. Okay. Another way to diagram it is you have these dotted lines. When you combine these two atomic orbitals to make a molecule, you have these two MOs, different energy levels, and you could populate them with the number of electrons that you have. Now, what's interesting about this is that we can calculate bond order. Remember bond order when we talked about resonance? A bond order simply is if it's a single bond, it's 1. If it's a double bond, it's 2. If it's a triple bond, it's 3. But we also saw bond orders when we had resonance that we had 1.5 bonds or 1 1/3 of a bond. We have like a hybrid between a single and a double. The same thing can be done with MOs, and we should get the same number, but we're going to calculate it a little bit differently now. The bond order when you use MO diagrams is 1/2 the electrons in bonding orbitals, and we are going to use MOs, so bonding MOs, minus the electrons in antibonding MO. Okay, look at this. We have for the math 1/2 2 electrons in bonding minus no electrons in the antibonding equals 2, and 1/2 of 2 equals 1. And yeah, it is predicted that H2 exists, and it's a single bond based on this bond order. Now, when we use valence bond theory, you know that this single bond is really a sigma bond made by the overlap of the 1s orbitals. But now we're looking at H2 in a different manner. We're looking at from the terms of MOs. So don't forget bond order, okay? That equation right there. Because we will have molecules that are impossible to make if they have no bond order, if the bond order is 0. So let me show you that. And we could say a molecule, and we're basically looking at diatomics. MO theory is pretty difficult to get a grasp on when you have bigger molecules. So for this video, I'm only going to restrict myself to diatomics, and a molecule or diatomic molecule exists if bond order is not 0. Okay. So let me think. 1, 2, 3, 4. Helium 2, neutral. Now helium still has those 1s orbitals. So we have helium, helium, and let me just use lines now. 1s, 1s. That's an H. Remember with helium it has 2 valence electrons. 1, 2, 1, 2. Those are your AOs, your atomic orbitals. But when you have MOs, you'll have an MO on the top, an MO on the bottom, and they will still have the same name. This will be sigma 1s, and this one will be sigma star 1s. So now your job is to populate those MOs with the 4 valence electrons of helium, because we have 2 helium atoms. 1, 2, 3, 4. So now when we're thinking about the stability of the molecule, we're only looking at the MOs, and we could figure out bond order. Bond order is 1/2 the number of electrons in the bonding MO minus the number of electrons in the antibonding MO, and that equals 2 minus 2 is 0, times 1/2 is 0. The conclusion here is that the bond order is 0, and this molecule cannot exist. And that kind of makes sense, or it does make sense, because helium is a noble gas, and you're not going to make it diatomic. But the thing is, what if we get rid of one of the valence electrons and we have He2 plus? Okay, these are very, even for me, I've been teaching this is still very unusual to me, all right? I've never worked with a He2 plus molecule, but theoretically, we can decide whether this exists or not. Because in this case, we have to pick one of the heliums to have a deficiency of electrons. So let me pick the one on the right, or the left, sorry, to be the one that's missing an electron. And we only have now one electron there. Because we know for a fact that for helium-2+, just from our work with Lewis structures, helium has 2 valence electrons, but you have 2 of them. Okay, so 2 times 2. But since it's plus, we have to minus 1 electron. So this is 3 electrons. And the 3 electrons can be shown in the atomic orbitals like this. It doesn't matter which one is the one that's deficient in electrons, which one lost. It's just that one of them has to lose an electron. Your MO, molecular orbitals. Again, when you mix 2 atomic orbitals, you get 2 MOs. And one of them still is going to be the sigma 1s, sigma star 1s. Now let's populate. 1, 2, 3. You're looking at this. The bond order is 1/2, 2 minus 1 this time, because we only have 1 electron in the antibonding orbital, and that equals 1/2. So you do have a half bond. He2 can exist, or you could say does exist, or however way you want to say it. I would say, yeah, can exist. I don't know for a fact if it's been made, but theoretically it can. It has a half bond, so it's not even a single bond. Okay, it's weaker than a single bond, but theoretically this can exist, the He2+. So since for now we are restricting ourselves to atoms that only have a 1s orbital, there's not much we can do in terms of examples. At home, what can you do? At home, you could try something like H2 minus, or H2 plus, or He2 minus. Okay, you could do all of these different combinations. Practice your MO diagrams and ask yourself whether that molecule can exist or not. Okay. We're going to look at some more complicated molecules in just a bit, but there's one last thing. As long as I have the MO diagrams up, there is a property, magnetism, that can be predicted based on MOs. So yeah, maybe I could also do that here. Magnetism. Okay, so that's another way to use MO theory. Again, neither theory is better than the other. It just depends on what you want to study and which one will best help you study those properties. For magnetism, we have something called paramagnetic and diamagnetic. Let me do paramagnetic first. A molecule is paramagnetic if in the MO diagram, and just the middle part, right? In the MO diagram, you have unpaired electrons, either one or more unpaired electrons. And this is what we know as magnets. This will be attracted to a magnet. So yes, let's say we have an unpaired electron here. Let's say we make He2 plus, we cool it so it's a liquid, and as we pass that liquid past a magnet, flow that liquid past a magnet, that liquid will be attracted to that magnet because it is paramagnetic. The opposite is diamagnetic, and that has no attraction to a magnet. So diamagnetic is if all electrons in the MO are paired. MO diagram are paired, so not attracted. Hence, so I can't actually make this one right here because He2 does not exist. But how about H2 gas? So if I could liquefy that and I flow it past a magnet, it will not be attracted because it is diamagnetic because all the electrons in the MO are paired. Okay? Okay, so keep those in mind. We want to know how to use the orbital diagram and MO diagram to figure out bond order and to figure out whether a molecule is paramagnetic or diamagnetic. Again, from the bond order, we could tell if the molecule can exist or cannot exist. Cannot exist. Let me show you actually a couple of pictures and then a more complicated diatomic molecule. The thing with this MO theory is that we are basically thinking of the electrons as waves. We're back to wave properties of electrons. For the valence bond, it's fine to think of them as particles. But when you think of them as waves and you're using the wave equations, when you bring two atoms together, let's say two hydrogens, those waves can either add constructively to make a bond or destructively to actually make an antibond. That's where we get the antibonding orbital, is that it accounts for the fact that waves can destructively add and you have no electron density in between the two nuclei. And they have shape. So here we have H2. These are not electrons, these are nuclei. But doesn't that look like a sigma bond where the electron density is indicated by a cloud, an electron cloud, and most of the time it is along the axis of the bond axis, on average. That is your sigma bond, and that is your sigma 1s MO. We've seen that already in this video. Here, we have the antibonding orbital, antibonding MO. And you notice that it's antibonding because there's no electron density that's holding the two nuclei together. Remember how I said that MO can be used to figure out reactivity? The idea is, if you know the shapes of the antibonding orbital, even if it's not populated, as you populate the MO, as you populate the antibonding, right? It's the one with the star, MO. You are weakening the actual bond that's in the bonding MO. This is a way to break bonds, in other words. And this is great for organic chemists because they could visualize what approach, if you could overlap these orbitals onto one molecule, you could visualize where is that antibonding orbital. Okay, so it does exist and it can be filled. I mean, it really can be filled because we saw it up here. It's filling right here. Weakening, right? Weakening a bond that would have been made if we had only these two electrons. Okay. The harder examples that I want to just briefly look over are the ones for the atoms in period 2. Now don't freak out. It's still the same setup, okay? But it's more complicated because the elements in period 2 have p orbitals, and they have electrons in p orbitals. So this is what I want to go over. Now there's different families. For the O, F, and N neon family, you use this diagram. And for the boron, carbon, nitrogen, you use this diagram on the right. I would not ask my students to memorize how to draw this diagram. what I would ask is, if you're given, for instance, C2, can this exist? And is it para or diamagnetic? So let me show you what I would do for this one, for C2. C and C. You know that C has 4 valence electrons. 1, 2, 3, 4. For the other carbon, 1, 2, 3, 4. If that C2 is not charged, you have a total of 8 valence electrons. And all you want to do is fill in your orbitals. They're the same orbitals, sigma 2s, sigma star 2s, but it's 2s now because we have the atomic orbitals 2s that are mixing. That's 1, 2, 3, 4. Now use Hund's rule, 5, 6, 7, 8. Now, don't worry how they figured out that some of these MOs are pi and some of them are sigma. You know what pi means. Pi means that the electron density making that bond is around the bond axis, not along the bond axis. Okay, and yeah, they are different for these two families. But these are our questions. Can it exist? Well, you use bond order. So we have 1/2, we have 1, 2, 3, 4, 5, 6. 6 electrons in the bonding minus 2 electrons in the antibonding. 6 minus 2 is 4 times 1/2 equals 2. So it can exist. Okay, so there can be a double bond between 2 carbons. Okay, is it para or diamagnetic? Every electron is paired. So C2 is diamagnetic. That is what I expect my students to be able to do when I give them the templates. Okay, when I give them the templates. Other professors want you to memorize the templates, but for my class, for now, don't memorize the templates. I will give them to you. You just have to understand how to fill in the atomic orbitals based on the number of valence electrons and how to populate the MOs. Now, of course, based on this template, I could say, well, what about O2, 2 minus? I can make them charged. You just have to add the right number of electrons, and I would do, what would I do? I would make one oxygen negative and the other oxygen negative as well. So when you combine them, it's a 2 minus. So let me just quickly do this. Oxygen has 6 valence electrons, but we have 2 of them. But we also have a charge of 2 minus, that's plus 2. That equals 14. So oxygen has 6, but if I have a negative, that makes it 7. 1, 2, 3, 4, 5, 6, 7. If I do the same thing for this oxygen here, I do have my total of 14. Check. 14 electrons, check. I have to fill the MO portion with 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yikes. Because I'm filling in some antibonding orbitals. 1/2. Bonding is 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2, 3, 4, 5, 6. So this molecule can exist with a bond order of 1. Just double check that I have all the electrons. Okay, good. And this one also is diamagnetic. Diamagnetic. Okay. That is MO in a nutshell. And then, yeah, that concludes Unit 7. It's a long unit, but we are looking at all the different ways to look at bonding. So, well, I think that's it. All right. good luck with your studies, and try the problems throughout these videos that I've said to do at home. Okay?